We'll get started with a brief overview of AI and deep learning use cases on third generation Xeon scalable processor supporting deep learning boost or the DL boost. And we'll go over a brief overview of the Xeon DL Boost roadmap, followed by the software solution stack offered by Intel, and spend significant amount of time around the performance optimization opportunities to unleash the capabilities of DL Boost, and then wrap up for today. All right, AI is everywhere and is one of the fastest growing and changing field. Third generation Xeon scalable processors supporting DL Boost feature leads the industry in terms of broad AI use cases across machine learning, deep learning, data analytics, and other AI categories with turnkey open source standards based optimized software. In today's session, we'll focus on how we approach to cater deep learning as a subset of these fastest growing segments with continuous innovation in both hardware and in software using third generation Xeon scalable processor system supporting DL Boost feature. So we have already seen deep learning making its impact in our daily lives, either directly or indirectly across a wide variety of use cases, and the possibilities going forward are almost limitless. For deep learning inference, the Xeon scalable CPU remains the most commonly used processor with built-in AI acceleration via DL Boost. An extensive optimized AI software stack that's built upon scalable open standard ecosystem, the one API, that can cater a wide variety of use cases, spawning edge, the network, and to the cloud. The third generation Xeon scalable processors is the Intel's highest performing data center processor with built-in deep learning acceleration to deliver outstanding performance generation to generation. And in addition to deep learning built-in acceleration, we do have other enhanced features that goodness that comes along with the Xeon third generation scalable processor platform. Specifically from an AI and deep learning perspective, the increased core count featuring up to 40 cores and significant memory improvements in terms of per core cache, as well as moving from our past generation Xeon scalable processor of supporting 6 channels, 2933 speed DDR to 8 memory channels at 3200 DDR speeds, combined with our optimized software solution stack, provides a significant boost for deep learning workloads across a variety of use cases. As you know, deep learning is one of the fastest growing and changing field, and it includes a wide variety of topologies, frameworks, as well as the industry is embracing going from higher bit precision, such as floating point 32, FP32, to lower bit precision, such as integer 8 or int 8, with minimal accuracy loss. Third generation Intel Xeon scalable processors offer the built-in DL Boost capability in terms of accelerating low precision integer 8 math. As we discussed, going from a floating point 32 to an integer 8 precision, we get significant amount of performance boost with a very similar or very minimal accuracy loss for inference use cases. The key benefits of accelerating the low precision integer 8 inference is derived from the inherent nature of the deep learning workloads. Many of deep learning operations are memory bound operations. So going by a lower precision integer 8 helps us to permits us to use better memory utilization in the system in terms of better cache usage, as well as a reduction in memory bandwidth bottlenecks. And this allows more data to be moved quickly and so that the compute resources are efficiently utilized and maximized. The second aspect is in terms of lower precision multipliers requires less silicon area and they burn less power. That helps to keep the hardware to execute more number of operations per second, thereby accelerating workloads in a further manner to get more performance at a workload level.
So ultimately in deep learning, there's so many math instructions and calculations you have to do that optimizing and taking shortcuts, from a calculations perspective is clearly important. On the other side, a lot of your competitors are kind of using a much higher amount of cores in order to achieve this as well, considering that the high level of parallelization is a priority. How do you see the third generation 40 cores kind of compete with other deep learning CPUs where there are thousands of cores?
Yeah. So, great question. So there are a couple of things. One is like, as you can imagine, Xeon runs AI as part of a workload in addition to other general purpose workloads in the that's most popularly used Xeon as a platform of choice. So that's one thing. The second aspect is in terms of the acceleration, the built-in acceleration offered for the in the third generation Xeon scalable processor is really providing a tremendous improvement in the throughput, like that we will walk you through in the later part of the section in terms of how we translate the even at a 40 core count part, how our performance are looking really significantly better. And as part of yesterday's keynote, you might have seen some of the collateral around like how we are our performance on third generation Xeon scalable processor is comparing to competition with the higher core count offerings as well. We do have a significant leadership, and this is one of the key differentiating features on the in the market, wherein like in a data center with having built-in acceleration. And we do have some all of our those proof points from the keynotes as part of the collateral. As we walk through the performance section, you'll see the links on the bottom, as well as more performance insights as well.
Okay, thank you.
Okay. Great. Okay, thank you. Here's the a quick overview of our Xeon DL Boost roadmap. In our first generation Xeon scalable processors, codenamed Skylake, provided AVX 512 based FMA units for efficient acceleration of floating point 32-bit data type. Then our second generation Xeon scalable processors, codenamed Cascade Lake, featured the first instantiation of built-in acceleration using Intel Deep Learning Boost, delivering like significant acceleration for the integer 8 precision. And our third generation processor offers more performance with built-in DL Boost acceleration, along with the significant amount of new software optimizations and turnkey solutions that delivers higher AI performance relative to our previous generation, second generation Xeon scalable processors. And going forward, Intel is, as we discussed, AI is a key part of the workload mix in a data center and across edge to the data center. So going forward, Intel we expect it to have more performant built-in accelerators with advanced matrix instructions and others to provide a significant performance boost on Xeon scalable processors that can help with workloads either as part of AI as being a part of the workload mix, or AI having a more presence in terms of the workload in the data center or at the edge. All right. So the third generation Intel Xeon scalable processors supporting the deep learning stack is the software stack is a very highly integrated, highly performant and optimized open source standard based software stack. The combination at a platform level is what gives us a significant performance boost. In terms of Intel's contributions, we provide fundamentally three key ingredients to accelerate inference workloads efficiently. We have been doing extensive pathfinding and industry research to come up with methodology for translating floating point 32 FP32 to integer 8 support with minimal accuracy loss, and have come up with a significant amount of tools such as like a scalable quantization tools that helps the ecosystem and the industry to improve productivity in terms of translation from higher bit precision FP32 to lower bit integer 8 precision seamlessly across wide variety of models and use cases and across popular frameworks. The second aspect is in terms of the framework optimization support. So this involves extensive optimizations to popular open source frameworks such as TensorFlow, OpenVINO, PyTorch to leverage the key primitives offered by one DNN library, uh, which is an open source Intel's contribution one as part of Open Standards One API. It's an open source entity that provides optimized deep learning primitives that abstracts the actual hardware ISA nitty-gritties for ease of use and to enable quick turnkey acceleration for wide variety of the primitives supported by this popular topologies in the industry. Thereby, it's a turnkey solution for customers to enable and embrace the features offered in the hardware. In addition to the above ingredients, as you may know, we significantly partner and co-engineer with key stakeholders on optimal solution enabling using the above ingredients across wide variety of use cases that we'll be discussing shortly in the later part of the presentation. With this, I would like to invite Shamima to talk about deep dive onto our performance optimizations opportunity across this stack and with example use cases that where we see the significant performance gains.
Thank you, Rajesh. So I am going to talk about performance optimization opportunities and how the performance look like on third generation Xeon. So let's see some key points to keep in mind as we go over the performance. Third generation Xeon will support up to 40 cores, and there is also improvement in cache architecture. So per core cache improved from second generation to third generation. Also, from second generation to third generation, memory channel got increased from 6 to 8. Also, third generation support 32 megahertz DIMM speed. So this helps to improve memory bandwidth as well as memory storage capacity. With the DL boost feature, along with computational benefits with larger core, with this memory bandwidth increase, it helps to reduce memory footprint reduction with higher memory bandwidth and provide performance boost to memory-bound workload. Let's look at performance gain. For deep learning workloads, we will show performance for variety of use cases, say image recognition, object detection, recommendation, and natural language processing. For performance, we have considered two test scenarios. One is batched inference, other one is real-time inference. Here is second generation to third generation performance boost. So if we see here, we can see up to 1.7x performance boost for more compute and more memory storage and bandwidth for third generation Intel processor. And here is real-time inference. So here we can see the performance boost can go up to 1.59x while moving from second generation to third generation. Let's look how low precision benefit to Baidu's paddle optical character recognition application using DL boost feature on third generation Xeon platform. This optical character recognition application is used for remote identity authentication, financial and tax reimbursement, document digitization. Paddle addresses this speed leverage through low precision inference of paddle models along with DL boost acceleration from Intel platform. Baidu's optical character recognition model use image classification model such as ResNet 50 as the backbone. So here, if we see the left curve, there is a performance benefit we can see from FP32 to Int8, where it provides boost on 3.56x performance boost from FP32 to Int8. This is the benefit of getting low precision inference. Let's take a look at another example, an application from Alibaba, where natural language processing use case use transformer model for end-to-end machine learning platform for AI. So low latency and high throughput are keys to transformer success, and low precision inference is a promising technique to meet such requirements. So by using Intel DL Boost feature for Int8, if we see here, both for second generation and third generation, we can see more than 3x performance boost while we go to low precision inference. If we consider second generation to third generation, for Int8, we can see 42% performance getting improved for this transformer model for Alibaba's requirement. In addition to that, while we are converting FP30 to Int8, the accuracy loss is 0.4%, which meets customer need. Let's see other example, Tencent Games. Tencent Games is building a new 3D digital face construction solution. Initial adopters are using this solution in game character generation and character model shifting to bring gamers a smoother gaming experience. For this task, a network named Position Map Regression Network is being used, and this is also converted from FP32 to Int8. This network deployed on third generation scalable processor. And if we consider only FP32, the performance from second generation to third generation boost up 53%. And while we convert it from FP32 to Int8, we can see 4.23x performance boost with Int8 for this network used for character generation. Here, the accuracy loss from conversion of FP32 to Int8 is 0.0001. So we are getting a more than 4x performance boost with very minimal accuracy loss. This speed up resulted in significant savings in modeling time and also improved efficiency for game development with character modeling tasks. So far, we have seen performance proof point. Let's look into how we are achieving the performance. And so AI deep learning models characteristics are very diverse, and performance improvement depends on the nature of the models. So here I am showing a few of the model applications and the category of the networks. So if you see image recognition, object detection, image segmentation, these are primarily convolution neural network. For natural language processing, it is long short-term memory or transformer, recommendation system, multi-layer perceptron, and embedding layers. For speech data generation, that is both the recurrent neural network, generative adversary network is got used. So based on the nature of the models, the model can be compute intensive, memory bandwidth intensive, memory storage intensive. So let's take a look how this model can falls into this category. So if you see the right chart, it is denoted operation intensity for each type of network. So higher operational intensity means it is a compute intensive workload. So more core can benefit the performance, but if the compute operational intensity is lower, that time it becomes more memory sensitive and memory bound, where it requires high memory bandwidth as well as storage. So for example, if you see for embedding, operation intensity is very low, it makes it memory bound. And also, if you see, it also requires a lot of storage capacity as well. This makes it highly memory bound workload.
So if there are all these different diverse AI models in practice out there, are they being mixed in customer use cases as well? So does a customer need a flexible platform, or would they be able to build a special purpose platform to match the needs of a specific application that's using only one of these AI models?
So, good question, Stephen. So, this is one of the good example of the general purpose platform. So, where a mix of workload, where it may not need a very large number of compute, like CNNs, if there is kind of embeddings or recommendation system kind of models are there, which requires high memory bandwidth and memory storage capacity. So for those kind of applications, we can see that it may get benefit from CPUs.
Yeah, I think some of these workloads are in the real world, Stephen, by working with some of our key customers. What we have observed is the real memory footprint is so large, like that's one of the very significantly helpful feature from the CPU side of things, having such a vast amount of memory close enough to the compute. And also the models as well as the mix of the workloads. A lot of times, as we saw, AI is very pervasive across wide variety of use cases, right? So it's like AI becomes like an application on top of different use cases, like for example media analytics or any recommender systems and other things. So thereby having a general purpose compute and having AI as part of it, so the mix of having them together with a large memory footprint, it naturally favors like CPU becomes like an ideal choice of handling the mix of these different models and workloads together.
This might have connected the dots for me on another question I had, and that's with the software and the API. Is it these diversity of AI models the reason that you need the API? Are you using that to tweak the CPU for each one of these specific use cases and AI models? Is that where that comes in?
So in terms of the APIs is predominantly in terms of ease of use and turnkey solutions. Thereby, it provides a couple of different things. One is like in the most predominant, given the fast-moving world and the way the industry is going in faster aspect of embracing and deploying new models into the, for example, when we translate it to BERT and other from JNMT and other things, right? So the APIs provides a capability of abstracting the hardware nitty-gritty details for ease of use to integrate into the popular frameworks and platforms. The second aspect is the APIs also have, like in a moment, Shamima is going to go into deeper details in terms of some of the capabilities wherein like when we can combine operations, which we call the operation fusions, that way we can improve the network's overall compute capability in a fused manner. We can mitigate quite a bunch of memory bottlenecks and memory capacity issues as well, that by combining the operations. So that's where the other aspect where the open standards based API helps a lot actually.
So in addition to that, so there are two types of optimization, or I will go through it. So the framework optimization, that is general across the models. So any type of model requires that optimization, can make use of it. Other one is model specific quantization or optimization, that can be model specific or varies from case by case. But APIs and framework optimization is generally applicable for varieties of use cases.
I have a follow-up question on the software. So in order to take advantage of the new instruction sets and all the features that the new CPU is providing, do you provide like Intel compilers and Intel VTune and the whole tool chain to help optimize code that you have written in the past? And then maybe a second question attached to it is that obviously, this is true for the frameworks as well, right? So all the frameworks you mentioned earlier, do they already recognize the third generation of Xeon CPU, or is that still a work in progress?
Excellent question, Frederick. I think we're going to talk about a little bit more in the upcoming few slides. It's a good segue for us to lead us there. Short answer is yes. We do offer all that you're referring to in terms of optimal compiler, the patches for operating system to recognize, and the hardware DL boost feature, and tools to collect telemetry in terms of identifying bottlenecks in the microarchitectural as well as at the software layers. All are available for ecosystem. Yeah. In addition to that, we also have out-of-box models that can demonstrate these values that customers can really, and users can really see the performance and integrate into their workload mix with ease of use.
Can we talk about those customers for just a minute? So, for example, there are two different methods you could take. You could build out architectures that are specific to doing machine learning and AI, or you could leverage an existing infrastructure like a Gen 3 platform. Can you talk about what customers you're referring to when you talk about the Gen 3 potential customer? Are they the folks that are using the Intel processor for general purpose use and they just need some additional capabilities, or are these folks that have very specific workloads that are now thinking about using the Intel platform? Because I see those as two different use cases.
Mm-hmm. Yeah, absolutely. So in terms of for customers, it's regarding the two aspects that you're looking into is a nice perception. So in terms of existing customers who are using Xeon as a platform of choice for a variety of general purpose workloads and embracing the AI disruption and analytics disruption in across a wide variety of use cases, it becomes a natural affinity point for them to take advantage of DL Boost. For customers who are translating from a different model, who are focusing on from a different dedicated architectures, looking for primarily targeted on AI side of things, and who are willing to onboard into the Xeon side of things, is also happening. That what we have seen for a couple of reasons that I think Shamima mentioned in terms of the more newer models, especially, and the most popular workloads that we observe in a data centers type of scenarios like recommender systems and natural language processing, which we interact with everyday use cases, right? They are getting more and more in terms of both affinitized towards more memory bound in terms of both capacity as well as in terms of the latency aspect as well, and bandwidth sensitivity. So for real-time inferences, when you want to have a larger lookups that you need to do, as an example of an embedding scenario with a recommender system, where you need a larger footprint of having a bigger embeddings to be retained, and you need a very faster lookup to provide a real-time inference recommendation. So that motivates quite a bunch of people to also translate from other architecture to getting into general purpose and to Xeon side of things. And as we said, like AI is kind of revolutionizing across wide variety of mixes, so it becomes like a part of the workload in majority of scenarios. Yeah. And also, we haven't, in this specific session, we haven't focused much on the other goodness of Xeon DL Boost that's going to be talked about by our peers momentarily in the later part of the sections. Like when we have like the SGX or software guard extensions that provide significant capability in the hardware accelerated manner for confidential computing, which is another disruption that's happening in the industry by maintaining the privacy preserved confidential computing. So those aspects, along with the deep learning boost acceleration from a platform perspective, if you see, that is another enticing aspect for most of customers to translate and adopt more Xeon scalable processors.
Let's see how at the software optimization that helps to boost performance for these diverse characteristics of model. So if we see here for OS level, we can use performance governor and NUMA locality to provide an additional performance boost. On next level, we have one DNN math kernel library which is specialized for deep learning in operator optimizations. Third one is framework optimization, where there is hyperparameter tuning, graph optimization, and multiple operator fusions can provide us extra benefit. And finally, we need to have the model quantization, that is conversion of FP32 to Int8 to get most benefit from Intel DL Boost feature. And Intel provide automatic tools for quantization as well. So let's take a look for each of the features. So for CPU scaling governor, this can be operate in two modes. One is power save mode and another is performance mode. So power save mode sets CPU statically to low frequency to save power. On case of performance mode, it sets CPU statically to higher frequency, so it can perform best. So we suggest for deep learning workloads, the CPU from OS is good to set on performance mode. Other one is NUMA locality. So let's see, consider this is a Ice Lake third generation scalable processor, and it is a two socket system, socket 0 and socket 1. So while socket 0 running workload in socket 0 and fetching the data from memory of socket 0, the memory socket latency is 85 nanosecond. But if the cores in socket 0 try to fetch data from socket 1 memory, then it is called remote socket memory latency, and this is around 139 nanosecond. So if we see this one, local socket memory is less expensive. So if we bind the workload particular to the socket to local, it can help to improve performance. So there is a command to do that, and this is numactl command, where C belongs to CPU node, that is socket 0, and -m belongs to memory binding, that is membind. It's also to socket 0. So if any command line while we are running, if we add this to local to communicate locally between code to memory, then it helps us to improve performance. The next one is Intel One API Deep Neural Network Library. This helps improve productivity and enhanced performance for deep learning frameworks. So the benefits of this library is it can support multiple data type format. It supports FP32 data type as well as low precision format, FP16, bfloat16, int8. Along with supporting different data types, one DNN library implements also many required operations that is required for deep learning. For example, convolution, matrix multiplication, different types of activation functions, and for example, long short-term memory cells as well. The third benefit from using one DNN library we can use is it automatically detects Intel deep learning feature from the platform, and it can help to accelerate inference performance. Now, framework optimization. So Intel provides optimized framework. For example, Intel optimized TensorFlow operations. So here for Intel TensorFlow optimized framework, with this one, the user doesn't need to change any in their neural network model and realize performance gain with their existing Python program. It helps to also eliminate unnecessary and costly data layout conversion. Other important aspect is graph optimization, where multiple operations can be fused together, and thereby we can efficiently reuse the cache on CPU. So this helps to provide additional performance boost. In addition to graph optimization, hyperparameter tuning is also important, as the threading parameter or threading model varies from CPU to CPU, SKU to SKU, like 28-core CPU to 40-core CPU. So Intel provides automatic tuning called Tensor Tuner for TensorFlow hyperparameter tuning. This tool can read the configuration automatically from the system and do the tuning accordingly. And next one is Intel Low Precision Optimized tool. So for use of Intel DL Boost feature, we need to convert the model from FP32 to Int8. For ease of scalability with a different criteria of accuracy, Intel introduced this Intel Low Precision Optimization tool, where it can generate a automatically Int8 model with predefined accuracy loss. So this is a simple block diagram. Here is the config file. So the tool's input will be a FP32 model, and in the config we can define how much accuracy loss we intend to see. If 0.1%, 0.2% to 1%. And then we launch this tool and it will automatically generate Int8 model. This is the inner working of the LPOT tool. There will be tunable configurations for the model, that which layer to be quantized, how much it need to be quantized. Then it will pass through a quantization and it will go through some evaluation, whether it is meeting the criteria or not. Based on if it is meeting, then we will stop there. But if it is not meeting, then it will go through this loop again until it meets the predefined accuracy loss that user wanted. So all of the software stack I talked about, this multi-level optimized software, this solution are ready and can be found at Intel Model Zoo. So there are already pre-trained models for multiple use cases that I showed earlier for performance, and also the pre-built containers are there for user easiness. And reproducing the performance benchmark is a two-step process there. We just need to download the model, Intel Model Zoo branch, and then run the workload-specific container using this command line. It is available both for batch inference and real-time inference. And for each of the model, we do have containers for ease of use. So we have seen significant performance boost from second generation to third generation Xeon for AI. And as well as other key features. This makes it the platform of choice for general purpose compute. We also provide multi-level software stack to achieve performance boost using DL Boost. These include Intel Model Zoo, Low Precision Optimization Tool, Optimized Framework, OpenVINOS Toolkit, which are ready to use, and we can get benefit from third generation Xeon. In summary, we are providing the performance and flexibility to infuse AI into multiple applications from edge to cloud. Thank you.
Thanks, Shamima. And just one more comment, just to reiterate, in terms of as we started the discussion. So in terms of beyond deep learning, we also, Xeon scalable processors have both capabilities in terms of hardware as well as in terms of software ecosystem that we are providing, similar to deep learning, what you saw, for across wide variety of AI segments in terms of machine learning, analytics, and other AI categories as well, that spawns across from edge network to the cloud.
So right now you have a maximum of 2 sockets. Do you have plans to provide more sockets?
So in the past we have had variations in Xeons where that we support that can scale up to 8-socket scenarios, and also we do have in future we do have that capability in terms of based on the customer needs and the market needs in terms of the scalability from going beyond like 2-socket from 2 sockets to 4 and 8 sockets in a more modular fashion, so that it can be scaled up or scaled down from an infrastructure provider. Yeah.
I guess just maybe to add on that, not for Ice Lake server, it's going to be a 2-socket platform, but we do have our 3rd generation Xeon servers that do scale with the Cooper Lake, and they could go up to 8-socket as well.
We also got a glimpse in this presentation of a next generation, or a suggestion of a next generation platform that might support even more AI optimizations, but I imagine that there's probably nothing you can say about that at this point.
Yes, Stephen. Other than it's going to be more performant and will make significant improvements in both hardware and software. Yeah.